Hi everyone, welcome you all to this lecture about minimum spanning tree. This is C. Karpagavalli, Assistant Professor, Department of Artificial Intelligence and Data Science, Ramco Institute of Technology, Rajabalayam. Before getting into the topic, we need to understand what is minimum spanning tree. A minimum spanning tree is a subgraph that connects all the vertices of the main graph with the least possible edges and the minimum cost without forming cycles. This is very important. Without forming cycles, we need to create a subgraph that connects all the vertices of the main graph with the least cost edges. This is the sample graph with the minimum weight 21. There are two types of minimum spanning tree algorithm. Prim's minimum spanning tree algorithm and Kruskal's minimum spanning tree algorithm. Let's see the types one by one. Prim's minimum spanning tree algorithm is one of the efficient methods to find the minimum spanning tree of a given graph. The Prim's algorithm begins from a vertex that is set as a root and walks through all the vertices in the graph by determining the least cost adjacent edges. Prim's algorithm. The inputs taken by the algorithm are the graph G of V, E, where V is the set of vertices and E is the set of edges and source vertex S. The output is the minimum spanning tree of a given graph G. The step 1 of the algorithm is declare an array visited to store the visited vertices and add the root node to the visited array. Then check whether the adjacent vertices of the last visited vertex are present in the visited array or not. If the vertices are not in the visited array, compare the cost of the edges and add the least cost edge to the output spanning tree. Then adjacent unvisited vertices with the least cost edges added into the visited array and least cost edges added to the minimum spanning tree output. The steps 2 and 4 are repeated for all the unvisited vertices in the graph to obtain the full minimum spanning tree for the given graph. Finally, we need to calculate the cost of the minimum spanning tree obtained. This is the graph. We are going to construct the minimum spanning tree by using Prim's algorithm. Solution. In step 1, we need to create a visited array to store all the visited vertices into it. The root is mentioned as S. So among all the edges that are connected to the root S, we need to find the least cost edge. So among all the edges, the least cost is S to B. So this is added into the output graph S to B. Then the output array contains S, B vertices. Since B is the last visited in the output spanning tree, we need to calculate the least cost edge that is connected to the vertex B. B to A has the weight 9, B to C has the weight 16, B to E has the weight 14. Among these edges, B to A has the minimum weight. So this is added into the output graph B to A. So the vertex A is added to the output array. So V contains S, B, A. Since A is the last visited, check for the least cost edge that is connected to the vertex A. A to C has weight 22, A to B has weight 9, A to E has weight 11. So among these edges, A to B has the minimum weight. Already we have added the edge into the graph A to B. So check for the next least cost edge. So the next least cost edge is A to E. So the A to E is added into the output graph. The vertex E is added to the output array. So the output array contains S, B, A, E. Since E is the last visited, check for the least cost edge that is connected to the vertex E. E to C has 18, E to D has 3. Among these edges, E to D has the minimum weight. So this E to D is added to the spanning tree. So the output array contains S, B, A, E, D. So this is the output of the previous step. So the edge E to D is added into the output spanning tree. The vertex D is added to the output array. Since D is the last visited in the output spanning tree, check for the least cost edge that is connected to the vertex D. D to C has weight 15, D to E has weight 3. Already we have added the edge D to E, so we have to check for the next least cost edge. So the next least cost edge is D to C. So the D to C is added into the output graph. The edge C, the vertices D and EC is added to the output graph. So V is equal to S comma B comma A comma E comma D comma C. All the visited vertices should be added into the output array. All the edges should be added into the output spanning tree. Without forming cycle, we need to create the subgraph. So this is the subgraph for the given graph. It contains all the vertices, that is S, B, A, E, D and C. All the vertices are included in this subgraph, then without forming any cycle. So this is the final output of the given graph. So the minimum spanning tree for the given graph with the cost is 46. 8 plus S to B 8 plus 9, A to B is 9, then A to E is 11 plus D to D is 3, then D to C is 15. So adding all these weights, the cost is 46. So that's all about the Prim's minimum spanning tree algorithm. Let's see the Kruskal's minimum spanning tree algorithm. The Kruskal's minimum spanning tree algorithm is one of the efficient methods to find the minimum spanning tree of a given graph. The algorithm first starts from the forest, which is defined as a subgraph containing only vertices of the main graph, adding the least cost edges until the minimum spanning tree is created without forming any cycle. In minimum spanning tree, we need to create a subgraph without forming any cycle. That is very important. So Kruskal's algorithm also, we need to create the subgraph by using the Kruskal's algorithm. We need to create a subgraph without forming any cycles. The Kruskal's algorithm has easier implementation when comparing to the Prim's algorithm, but it has higher complexity. Kruskal's algorithm. The inputs taken by the Kruskal's algorithm are the graph G of V comma E, where V is the set of vertices, E is the set of edges, and source vertex S. The output is the minimum spanning tree of the given graph G. The step 1 of the algorithm is sort all the edges in the graph in an ascending order. That is very important. Sort all the edges in the graph in an ascending order and store it in the array edge. Then step 2, construct the forest of the given graph on a plane with all the vertices in the main graph. So construct the forest of the given graph with including all the vertices. Then step 3, select the least cost edge from the edge array and add it to the forest of the graph. Then mark the vertices visited by adding them into the visited array. Repeat the steps 2 and 3 until all the vertices are visited without forming any cycles. When all the vertices are visited, the minimum spanning tree is created. Finally, we need to calculate the minimum cost for the output spanning tree obtained. This is the graph. We are going to find out the minimum spanning tree by using Kruskal's algorithm. This graph is having 7 vertices A, B, C, D, E, F and G. So from this graph, we are going to find out the minimum spanning tree by using Kruskal's algorithm. In solution, the first step is sort all the edges in the given graph in an ascending order and store the values in an array. So this is the edge array. It is having all the edges with the weight. The weights are arranging in an ascending order. So from this edge array, we are going to construct the minimum spanning tree. So then construct a forest of the given graph in a single plane. So the forest contains all the vertices in the main graph A, B, C, D, E, F and G. So all the vertices should be available in the forest. So from the list of the sorted edges, select the least cost edge and add it to the forest in output graph. So among these all the edges, the least cost is B to D, meaning the cost 5. So this is added into the output graph B to D. The visited array contains B, D vertices. Similarly, the next least cost edge is B2A with the cost 6. So this is added into the output graph. 6 A to B edges added to the output graph. The vertex A is added to the visited array. So the visited array contains B comma A comma B comma D comma A. All these visited vertices up to this we have to add it into the visited array. The next least cost edge is C to F with a weight 9. So add it to the output graph. So this C to F is added into the minimum spanning tree. Then the edges C comma F is added to the output array, visited array. So the visited array contains B comma D comma A comma C comma F. So the minimum cost is 5 plus 6 plus 9 is equal to 20. All the visited vertices should be available in the visited array. All the edges should be added into the minimum spanning tree. The next least cost edge to be added to the output graph is F2E with the weight 10. So here we are adding the edge F2E in the minimum spanning tree output. The visited array contains all the visited vertices B, D, A, C, F, E. So these are the edges we have visited up to this. So all these edges should be added into the visited array. So the minimum cost up to this is 30. 5 plus 6 plus 9 plus 10 is equal to 30. The next least cost edge that is to be added into the minimum spanning tree is B2C with the weight 11. So here we are adding this edge B2C into the minimum spanning tree. So all these vertices, visited vertices should be available in the visited array. The visited array contains B, D, A, C, F, E. All the visited vertices should be available in the visited array. The minimum cost up to this is 41. 5 plus 6 plus 9 plus 11 plus 11 is equal to 41. So up to this the minimum cost for the minimum spanning tree is 41. The vertices B2C is the edge B2C is added finally. Then the next least cost edge that is to be added into the output graph is F2G, final edge. So here we are adding the edge F2G into the output spanning tree. So the visited array contains the vertices G, B, D, A, C, F, E, G. So all the visited vertices should be available in the visited array B. The minimum cost is the 53, that is 5 plus 6 plus 9 plus 10 plus 11 plus 12 is equal to 53. So this is the final graph, final minimum spanning tree for the given graph by using the Kruskal's algorithm. So here we should add all the cost for adding the minimum spanning tree. So all the visited vertices should be available in the visited array. So the final cost minimum spanning tree for the given graph is 53. So up to this we have seen about the minimum spanning tree and the types of minimum spanning tree, that is Prim's algorithm and Kruskal's algorithm. Next is applications of the minimum spanning tree. Number one is laying of communication links between any two stations involving a cost. Then construction of highways or railroads spanning several cities. Then designing local area networks involving the minimum spanning tree. Then laying pipelines connecting offshore drilling sites, refineries and consumer markets. Then suppose if you want to apply a set of houses with electric power, water, telephone lines, sewage lines. In order to reduce the cost, we can use the minimum spanning tree to connect the houses. So thank you all. Thanks for watching.